Okay, so now that you've done the little book activity, can anybody give me a good definition of what a limiting reactant is, or defining limiting reactant? Anyone? How would you describe limiting reactant? Yes?
The least amount of the product.
Well, it does produce the least amount of the product. How would you describe the reactant itself? The reactant that is used up. What else could we say? The reactant that you run out of. The reactant that runs out first. And if you want to get real technical with the good chemistry term, you would say it's the reactant that is completely consumed. So that would be a good way to say it. You might see it phrased that way in problems where they talk about being in excess or being completely consumed. So the reactant that is completely consumed, used up, or runs out. Okay, any way of phrasing it like that should be fine. Now, how would you define excess reactant? And sometimes they call it an excess reagent. Don't be thrown by the word, it means the same thing. Reagent is the same thing as a reactant. Anybody want to describe how you define excess reactant? Yes?
Whatever is left over
Well, it is a reactant that
is left over.
that is not completely consumed, and yes, there is leftover, or there's extra still in the reaction vessel or the beaker or whatever you're using to do your reaction. This one, there's leftover amount, okay? So the reactant with extra left over, not completely consumed. Those are very good ways of phrasing the definitions of those things. Now on your sheet here, it gives you some notes and examples to follow, but I'm going to go ahead and go straight to number 1 and we'll work it together. And this will help you work number 18 on the other sheet if you haven't already. All right, so there's more notes here, but I'm going to explain all of these as I work through problem number 1. What you should recognize here, though, first of all, when you're given a problem, this is going to be different than regular stoic problems in and of the fact that they're going to give you 2 numerical values of the reactants to begin with. Like we have 100 grams of sodium, we have 100 grams of the iron 3 oxide. They give you amounts of both reactants. When they do that, you should recognize it automatically as being a limiting reactant problem. So if they give you both amounts of the reactants, you're going to have to do both of them because you don't know which one runs out first. So you have to solve for both. So know that anytime they give you amounts on both reactants, it's a limiting reactant problem. But before we begin, what do we have to do? Balance, so let's balance. And yes, up here already, we would probably want to start with balancing our oxygens first and put a 3 here. That way we know our sodium's going to get a 6 here. And then we'll fix our irons with a 2 here. Are we in agreement?
Yeah.
With our balancing here? All right. So I'm going to set up both of my reactants. And the other thing that you need to pay attention to in these problems is, it tells me my reactants, but it also basically words it later on. It wants the limiting and excess reactant, but then it's also going to tell me which product to work to. How many grams of the sodium oxide could be produced? So this right here is telling me which product to work both of the reactants to. Because I could do all and work it all out to iron, and I could identify the limiting and I can identify the excess, but In the end, then I have to do a third track to figure out the sodium oxide. So it's much easier if I identify which product it's working to before I start, and then I'm going to work both of my reactants to that product. So let's start over here. We have 100 grams of our sodium. We have 100 grams of our iron 3 oxide. Now I have to work them both to this guy, to the sodium oxide product. So when I have grams, I need to do what first? Change it to moles using molar mass. That's why you need your periodic table out. So what's the molar mass of sodium? 22.99 grams of sodium give me 1 mole of sodium. Now I can do mole ratio because I can do moles of sodium to moles of the sodium oxide. Looking at our balanced equation, we have 3 moles of our sodium oxide and we have 6 moles of our sodium. Now we can solve that one. I'm going to go ahead and set up the other one as well. Anybody with a molar mass on iron 3 oxide? What'd you say? 159.70. Let's carry it out to the hundredths, of course. That equals 1 mole of the Fe2O3. Good. Now we do the mole ratio. Moles Fe2O3 going to moles of Na2O. Once again, looking up here, this one is a mole of 1. And this one is a mole of 3. Good. And now we can solve them both. So let's go ahead and calculate. Anybody get the value for the top one? Yep. 2 point something? That sounds about right. Would you get 2.17? How many sig figs do we need to keep? 4. So what's that last digit? A5. Good. So this is moles Na2O. Now, bottom one, what do we get there? Anyone? Anyone? How many sig figs? How many sig figs?
1.88 moles.
How many sig figs?
7.
Oh, 1.87.
Oh, 8, 7.
8, 7, 9. Very good. Okay. 1.8794 sig figs. All right. Now that we have both of our mole value, we can compare numbers. Which one is the smaller amount of product? Down here, this is the smaller amount of product. So this is your theoretical yield in moles. This is in moles, of course. Most of the time, though, we have to go ahead and at the end calculate the theoretical yield in grams because when we're trying to do percent yield, the actual yield is always reported in grams. And we'll do that on the percent yield paper as well. So if this is the theoretical yield, because it has the least amount of product made, what does that tell me about this guy right here?
It's the limiting.
It is the limiting reactant, because it runs out first. It's completely consumed. How about this one right here?
Access.
That's going to be your access reactant, excuse me, because it's going to have leftover still in the reaction vessel or container, and you will have some that you have to calculate and figure out how much is left over. All right, now we've done this part. This is great, but we haven't finished this problem yet because it wants to know how many grams of the sodium oxide could be produced. So what do we do with this theoretical yield over here? We take it and do what? What do we need to do? Change it to, it wants, what does it want? Grams. So we're going to change it to grams. 1 mole Na2O equals how many grams? Who has the molar mass? Anyone? There's my gift to you. Those are your grams of sodium oxide. And how many grams would we make as our theoretical yield here?
Uh, 116.5.
116.5 is correct. Very good. So this is our theoretical yield that we would use if we were trying to calculate percent yield with an actual. All right, so that's the beginning part. We still have one more thing to do because we need to calculate the excess amount. Okay, now you can do it one of two ways. You can start with the theoretical yield and work it to the excess reactant, or you can start with the limiting reactant and work it to the excess reactant. So I'm going to show you both. You can pick which way you like better. Of course, I told you that I preferred to start with the limiting. I was programmed to use the limiting reactant. So my limiting reactant, I'm going to begin with its original amount, which was 100. I'm going to go ahead and change it to moles. Luckily, we've already calculated the molar mass here. It's 159.70 equals 1 mole. Then I'm going to do the mole ratio, but I'm going to go to the excess reactant. So moles of Fe2O3 to moles of sodium. And if you remember from the balanced reaction above, there were 6 moles of sodium for every 1 mole of Fe2O3. Now, because I was given the excess reactant in grams, I need to finish changing it to grams. So here, 1 mole of sodium is going to give me 22.99 grams off the periodic table. Now, what I'm calculating with this T-chart, this track, is the amount of the sodium that's actually used. This is what gets used up in the reaction. So, how much gets used? Let's calculate that. What do we get here? We get 86.37 grams of sodium. This is how much is used in the reaction. Now, what was the original amount of the sodium? So we started with 100 grams. This was the starting amount. We're going to subtract out the 86.37 grams. This was what was used. And then we're going to get our amount left over. Now do remember on subtraction, you have to look at place value. So we have hundredths and tenths. So I'm going to round my answer to the tenths. So this is going to be 13.6 grams of sodium left over. All right, left over. Now, that's one way you can work it. Limiting reactant to excess reactant, subtract from the original amount started with. The other way you could work it is starting with the theoretical yield. So you could start with our theoretical yield up here, this number. 1.879 moles Na2O. Okay? We're going to work this also to the grams of sodium. 1 mole Na2O. Actually, it's not 1 mole. What is it? It's 3 moles because we're doing mole ratio first. 3 moles to 6 moles of sodium. And then 1 mole of sodium is going to be 22.99 grams. Sodium, calculate that. 1.879 times 6 times 22.99 divided by 3. And guess what you get? 86.39. Oh, just so close to this value up here. Let's still do the subtraction. let's take the 100 grams, subtract the 86.39. Once again, still rounding to our tenths here because of significant figure rules. And you still end up with what? Still end up with our 13.6 grams sodium. So, you decide which way you like to calculate excess, because you can do it either way. And it's fine, just have to show the work. Start with the limiting or start with the theoretical yield, and then you can go there from there. Any questions?